Living creatures are amazing at building their homes from just about anything. But sea-dwelling creatures are particular wizards. Microscopic coccolithophores, coral-building algae, and giant snails engineer their own building material like magic by pulling two dissolved chemicals, calcium and carbonate, out of the water to form solid shells of, surprise, calcium carbonate. The reason those shells don't dissolve back into calcium and carbonate as soon as they're built is that ocean water is already holding as much calcium and carbonate as it can, so the mineral forms much more easily than it dissolves. At least that's the way it works near the surface, where the shell builders live. But at greater depths, the water isn't quite as saturated with calcium and carbonate, and thus calcium carbonate is easier to dissolve. So unlike shallow coastal waters where shells of dead creatures build up on the seafloor, out in the deep ocean, there's a depth at which calcium carbonate starts to break apart, and empty shells dissolve before reaching the bottom. This dissolving depth depends on the concentration of calcium and carbonate already in seawater. If the concentration is high, shells sink deeper before their calcium carbonate dissolves, and if the concentration is low, the dissolving depth moves closer to the surface, meaning the deepest intact shells begin to dissolve. But this is a feedback loop. Shells that dissolve add more calcium carbonate to the water, making it harder for other shells to dissolve and lowering the dissolving depth. Basically, chemistry in the deep ocean stabilizes the concentrations of calcium and carbonate in the seawater, which is why the upper part of the ocean is saturated with calcium and carbonate and perfect for shell building to begin with. Except we forgot to take into account the chemistry of another key part of the ocean, the atmosphere. At the ocean's surface, a small proportion of gases like oxygen and carbon dioxide dissolve into the water. Dissolved oxygen, for example, allows sea creatures to breathe. And when the concentration of the gases in the atmosphere rises or falls, so does the amount of gas dissolved in the oceans. If it weren't for the ocean's own balancing act, any incoming carbon dioxide would be bad news for shell builders, because more CO2 means less CO3. That might sound weird, but it's just the way the chemistry plays out. Dissolved CO2 molecules combine with water to form what's called carbonic acid, which in turn combines with carbonate to form hydrogen carbonate. Simply put, when carbon dioxide in the atmosphere increases, carbonate in the ocean decreases and shell building gets harder to do, at least for a moment. Given enough time, the physics and chemistry of the ocean will cause the dissolving depth to rise, and more shells on the seafloor will return their calcium and carbonate back to the water, restoring normal levels. There are situations where the oceans can't keep up this balancing act, though. For example, if so much carbon dioxide were added to the ocean that the dissolving depth rose high enough, all shells everywhere in the ocean might start dissolving. While possible, this is a lot less pressing than the risk that, for a time, CO2 levels change faster than the ocean can compensate, so that even if it would eventually stabilize and allow shell formation at the surface, it would take centuries to do so. During that time, the upper reaches of the ocean, where most of the amazing shell builders live, might become a barren wasteland. And speaking shellfishly, that would be a calamity. This episode of Minute Earth is supported by James Cook University, located in Australia near the Great Barrier Reef and next to inland tropical rainforests. Researchers at JCU study, among other things, coral reef ecology, ocean acidification, and the effects of the changing climate. To find out more about James Cook University and their courses in marine biology, zoology, aquaculture, fisheries management, ecology, and more, visit jcu.edu.au.